starting on the first page of the notes, Unit 4, Part 1. So again, we'll probably start Unit 4, Part 2, but we might not assess on it until the next term. So folks, this unit is all about quadratics. The nice thing is we've worked with quadratics before back in Unit 2 when we were talking about parent functions. So we know that they are shaped like parabolas. So the shape of a quadratic function is called a parabola. It either looks like a U or an upside down U. Going back to our previous unit with polynomials, in a quadratic function, the greatest exponent is 2. So the greatest exponent is 2, also called a degree of 2. Also, quadratic functions, that word function means it passes the vertical line test. So doing some reviewing of the last unit. So passes the vertical line test. And it will either look like this, which I call happy quadratic graphs, y equals x squared, or quadratic graphs, which have a negative in front of the squared term. And we have found that to be true with our transformation rules with vertically reflecting, but we also saw it in the context of polynomials. If we have a negative leading coefficient, our right arrow goes down. And if we have a positive leading coefficient, our right arrow goes up. So polynomial rules apply to quadratics, as do our transformation rules. A new vocab term that we're going to have in this unit is the axis of symmetry. What does that word symmetry or symmetrical mean to you guys? Give me an example of something that's symmetric. A circle, a heart, a butterfly. So something that's the same on both sides. The axis of symmetry is an imaginary line that divides the graph into two congruent or equal halves. So we're going to go ahead and draw that line in right here on this diagram. So we draw it as a dashed line, but it's not a bound line like we had with piecewise functions, but it is simply a line that cuts our parabola in half. The axis of symmetry, which I like to abbreviate as the A of S, axis of symmetry, has the following equation. X equals negative b over 2a. This equation you will have to eventually have memorized. It is a vital part for graphing. Now, if you're looking at that going, how is that a vital part for graphing parabolas when we haven't had to use it before? The key with how we've graphed parabolas in the past is we were able to use our transformation rules because they were in transformed format. In this unit, we are going to be looking at standard form equations for quadratics, which look like 8x squared plus bx plus c equals 0. So I won't be able to say that the c moves us up 4 or that the b vertically stretches it. Everything is joined by addition or subtraction, so our transformation rules will not apply. So just write no transformation rules. So if we don't know where that vertex is, we're going to have to use other methods for graphing. We're going to be using our axis of symmetry because that will lead us to our vertex. So the axis of symmetry is what helps us find the vertex of the parabola. And we can see that down on the bottom of this diagram. So my axis of symmetry will always go directly through the vertex. And the vertex will either be the maximum highest point or the minimum lowest point of the parabola. If it's a sad graph, then it has a high point maximum. If it's a happy graph, then it has a low point minimum. So that will be dependent on whether it's happy or sad, and based on if our leading coefficient is positive or negative. So maximum value comes from this type of graph that has a negative leading coefficient, and a minimum value comes from a positive leading coefficient, high point graph. So min, max. So let's do a little bit of practice with this standard form equation. Let's say I have y equals negative 2x squared plus 3x minus 4. Y equals negative 2x squared plus 3x minus 4. What would you say our A value is for this graph? Our A value is the negative 2. What's our B value? 3. And then our C value would be negative 4. So the A value is always paired with the x squared term. The B value is always paired with the x term, and the C value is always the constant term. Now, what can be tricky is sometimes you will have one or both of those. So let's say I have y equals negative 2x squared plus 3. Which term am I missing? The A, the B, or the C? The B term. So if you're like, well, what would I say is the B value for this one if I need to use my A and B values to find that axis of symmetry? What we would need to do is state that our B value is 0. So this is like having 0x plus 3. So have this on your radar that it could be missing your B value, you could be missing your C value, but you'll always have an A value. But you'll always have to have the A value because that's what makes it the quadratic. Okay. We're just in the new note packets. Remind me, I'll show you your test during work time. So folks, leading coefficient, going on to this definition right here. Your leading coefficient is simply the number in front of the term with the highest power. So just a review of the technical definition from the last unit. So the number in front of the term with the highest exponent, which for quadratics is always going to be the A value. So A for quadratics. Folks, go ahead and get out your calculators or grab one out of the cart if you don't have yours with you today. And here's another term that we saw in the last unit. The roots, the zeros. What's another way we can describe these? Roots and zeros. Oh, I already have it written over here. X-intercepts. These are going to be a large focus in this unit of how can we find the roots or zeros or solutions of a quadratic graphically by factoring and by using the quadratic formula. So your roots and zeros are always going to be x equals a number, but as a coordinate, the x-intercepts are a number and 0. And that's going to be something that we will be both solving for and pulling out as a key feature on our graph. So folks, we're going to practice just pulling these features out from an already graphed quadratic. If it asks for the zeros, that means the x-intercepts. So where is this graph hitting the x-axis? It's hitting at -6 and at 0. So normally I would have you state these as coordinates, but since we're going to be solving for these in a variety of ways, it will be most consistent if we say x is equal to -6 and x is equal to 0, but that refers to the points on the x-axis. Do you need to charge that? Oh. Next, our y-intercept. Folks, with the y-intercept, it's kind of like it was with polynomials where it's not always going to be a great point for graphing, but sometimes it will be useful to have it. So folks, what's our y-intercept for this one? 0, 0. The origin. Now for the axis of symmetry. So our axis of symmetry, that A of S, is a vertical line that cuts our quadratic in half. It's also useful to know that it will go directly through the vertex. So if I sketch that up from that vertex, from the starting point, where does it look like we have that vertical line? If this is -2 and that's -4 and this
-3.
Perfect, that's halfway between. So our axis of symmetry is at x equals -3. Folks, I want you to put an important box around that x equals because this is a vex equation. The equation of a vertical line is always x equals a number. So we can't just say that the axis of symmetry is equal to some value. It has to be the vertical line equation of x equals -3. Now, what can be confusing about this is a vertical line equation, but these are solutions for when the y value is equal to 0. So keeping these solutions or answers straight from this vertical line equation is something we're going to be working on over the next few days. So folks, what about the vertex? If I asked you for the coordinates of that vertex, what would you say they are? Perfect. So -3 and -2. One thing that I want you to notice is that your vertex has the same value as your axis of symmetry. This is no coincidence. Anything that lies on that axis of symmetry will have an x value of -3. So the vertex, which lies on that line, will also have an x value of -3. Ooh, let's see if we remember end behavior notation. So last unit coming back to haunt us. First, we look to the left. As x approaches -infinity, what's my function doing? And as x goes towards +infinity, what is that function doing? And we can read this directly from the graph. As we go towards -infinity, what is my function heading for? Infinity or +infinity. And then as we go towards +infinity, this side of the graph is also going towards +infinity. Remember, quadratics are even degree always, so the end behavior is either going to go up and up or down and down. Positive leading coefficient up and up, negative leading coefficient down and down. It all depends on what our a value is. Now, we don't have an equation for this graph, so there's no way of checking that, but on the next page, once we start looking at equations from the start, we'll start to pick up on that pattern. What's the domain of this graph? What x values are going to get covered? our graph goes all the way left and all the way right. Those arrows are going to keep going upward and outward. So my domain is all real numbers. So remember, you can either use the two-line fancy R notation, or what's the other way you can write it? Interval notation. So or negative infinity to infinity. Now the range, where do my y values start? Down here at the bottom at -2. And then are we covered up from -2 or down? Up. So y is greater than or equal to -2. If we wanted to write that in interval notation, we would say it starts at -2 with a bracket and is covered going to infinity. So for all quadratics, your domain will always be all real numbers. So if it's a happy quadratic, domain is all real numbers. If it's a sad quadratic, the domain will be all real numbers. The range, however, is affected by the happy or sadness of the graph, whether it's a positive leading coefficient or a negative leading coefficient. If it is a happy graph, our range will be y greater than or equal to the y value of the vertex. Whereas if we have a sad graph, our range will be y less than or equal to the y value of the vertex. So domain is always all real numbers, but if it's going up, y greater than or equal to, and if it's going down, y less than or equal to. So just be aware of the difference in inequalities between the two graphs. That concludes page 1.